So this is part 2 of my MCAT Organic Chemistry Review Reactions video. And in this video, we're going to cover the reactions that are usually taught in the second semester of organic chemistry. So we're going to go over the Diels-Alder reaction, benzene reactions, reactions associated with aldehydes and ketones, amines, carboxylic acid derivatives, and reactions such as like the aldol condensation reaction, the Acylation reaction, and even the Robertson-Annulation reaction, just to name a few. So let's begin. Let's get right into it. Now let's talk about the 1,2 and 1,4 addition reactions with 1,3-butadiene. So butane is 4 carbons, and we have a diene on carbon, a double bond on carbon 1 and 3. So that's a 1,3-butadiene. Now what's going to happen when it reacts with HBr? Now there's two products you can get. Let's call this carbon 1, 2, 3, and 4. The HBr molecule could add across the first two carbons across the double bond. Now, which element is more electronegative, hydrogen or bromine? Typically, as an element approaches fluorine on a periodic table, it becomes more electronegative. Bromine is more electronegative than hydrogen, so bromine bears the partial negative charge, and hydrogen bears the partial positive charge. Out of these two elements, the one that is more partially positive or less electronegative, that's the element that's going to go on carbon 1. The one that's more electronegative, in this case the bromine atom, is going to go on carbon 2, and the double bond is going to remain on 3 and 4. So this is called the 1,2 addition product. Now to draw the 1,4, the hydrogen is going to remain on carbon 1, and the bromine atom is going to move to carbon 4, and the double bond is going to be between 2 and 3. So this is the 1,4 addition product. Now usually the 1,2 addition product is usually the kinetic product, and the 1,4 product is usually the thermodynamic product. This isn't always the case, but generally speaking, it works out this way. The kinetic product forms faster. So under low temperature conditions, let's say if it was like -20 degrees Celsius, the kinetic product will be the major product. At high temperature conditions, let's say if the reaction was heated to like 80 degrees Celsius, the thermodynamic product is usually the major product. The kinetic product is the one that forms faster because it proceeds through a more stable carbocation intermediate. The element that is more electronegative, in this case the bromine atom, that's the one that attacks the carbocation. Notice that bromine is on a secondary carbon, which means that this reaction proceeded through a secondary carbocation. This bromine is on a primary carbon, so therefore that product proceeded through a primary carbocation. Now, so secondary carbocations are more stable than primary carbocations. So the one that generates or passes through the most stable carbocation, that is your kinetic product. That's how you identify it. Now, it turns out that this double bond is more stable than this one. Internal alkenes are more stable than terminal ones. So the thermodynamic product is usually the one with the most stable alkene. So how can we tell which alkene is more stable? So you need to count the number of R groups. So let's look at the kinetic product. What I'm going to do is I'm going to highlight the double bonded carbon atoms. Now, how many carbon atoms are attached to any one of those two double bonded carbon atoms highlighted in purple? There's only one other carbon atom, so therefore this is a mono-substituted alkene. It has only one R group. The more R groups an alkene has, the more stable it is. Now let's look at the other product. So here are the two double bonded carbon atoms. Now how many other carbon atoms are attached to those two carbon atoms highlighted in purple? So on the left side we have 1, and on the right side we have 2, so therefore this alkene has 2 R groups, which makes it more stable. Sometimes you might have 4 different products, and it might not be easy to see which is going to be the major product at high temperature or low temperature. The thermodynamic product is usually the one that has the most stable alkene, and the kinetic product is usually the one that passes through the most stable carbocation intermediate, and that's really how you identify it. But now let's focus on drawing the products for now. Let's do a few practice problems, and then we'll work on some mechanisms as well. Try this example. Let's say if we have 2,4-hexadiene, and let's react it with iodine monobromide. So bromine is more electronegative than iodine. So bromine has the partial negative charge and iodine has the partial positive charge. So iodine is going to act like hydrogen in this reaction. Now what you want to do is identify the 4 carbon atoms that are part of the 1,3-butadiene system. So that is 1, 2, 3, 4. Those are the 4 important carbons that we need to focus on. The other 2 we can just act as if it's not there, and we can add it later. So to draw the 1,2 product, oh, by the way, notice how this molecule has symmetry. Because it's symmetrical, that means that we're only going to get 2 products. If it's not symmetrical, if those double bonds are different, then we can get up to 4 products. So let's draw the 1,2 product. So just like before, we're going to put the element that is electropositive on carbon 1. So that's going to be the iodine atom. And on carbon 2, the one that's electronegative, or that bears the partial negative charge, that's going to be the bromine atom. And a double bond is going to remain between carbons 3 and 4. So this is the 1,2 product. And to draw the 1,4 product, we're going to put, well, iodine is going to stay on carbon 1, but the bromine is going to rearrange to carbon 4. And the double bond is going to be between 2 and 3. So that's the 1,4 product. Now, which one is the kinetic product and which one is the thermodynamic product? So which product would you get at low temperature and which one would you get at a high temperature? Now, notice that the double bonds are equally stable. Here are the 2 double bonded carbon atoms, and we have 1 carbon on the left that's attached to it and another one. So this has 2 R groups, which means that it's disubstituted. Now the same is true for this alkene. It also has 2 R groups. So these double bonds are equally stable. And if you look at the bromine, in both cases, it's on a secondary carbon. So even though these products are different, they both proceed through a secondary carbocation intermediate, and both alkenes are disubstituted. So their stabilities are about the same. So you can get both products at low temperature and at high temperature, which means that the kinetic thermodynamic situation doesn't apply here. So now it's your turn. Let's say if we have this particular reactant. So this is 3,4-dimethyl 2,4-hexadiene. And let's react it with ClBr. What is going to be the major product at high temperature? Let's say if we heat it to 100 degrees Celsius. So feel free to pause the video and try this example yourself. See if you can get the answer and then unpause it when you're ready. So let's begin. Let's identify the 4 carbons. Now the first thing you want to do is make sure that it has symmetry. So because this molecule is symmetrical, we can choose any double bond. So we're only going to get 2 products. So this is going to be carbon 1, carbon 2, 3, and 4. If we count it the other way, it's going to be the same. Now, which element is more electronegative, chlorine or bromine? Chlorine is more electronegative than bromine. It's closer to fluorine. So bromine is going to bear the partial positive charge this time. So the element that has the partial positive charge, we're going to put it on carbon 1. And chlorine, which is electronegative with respect to bromine, we're going to put that on carbon 2. So the double bond is going to remain between 3 and 4. So this is 1, 2, 3, and 4. So now let's draw the other product. This is the 1,2 addition product. So now let's draw the 1,4 addition product. So the bromine is going to remain on carbon 1, and the chlorine, we're going to put it on carbon 4 this time. And the double bond is going to be between carbons 2 and 3. So this is the 1,4 addition product. Now we need to identify which one is the kinetic product and which one is the thermodynamic product. So how would you do that? Let's identify which one proceeds through the most stable carbocation intermediate. So the element that is electronegative, that's going to be the one that's going to attack the carbocation because opposites attract. The carbocation has a positive charge, and chlorine, which is more electronegative, has the partial negative charge. So the carbocation was here on carbon 2, and the carbon that has the chlorine is a tertiary carbon since it's attached to 3 other carbon atoms. So now let's look at the other compound. The carbon that has the chlorine is attached to 2 other carbon atoms, so therefore it proceeded through a secondary carbocation intermediate. Tertiary carbocations are more stable than secondary carbocations, so that means that what we have here is the kinetic product. Now let's look at the alkene stability. So let's analyze the double bonded carbon atoms. How many carbon atoms are attached to those 2 carbons indicated in red? So here we have 1, 2, 3, which means that this is a tri-substituted alkene because it has 3 R groups. Now looking at the other double bond, how many carbon atoms are attached to these 2 double bonded carbon atoms? So here we have 1, 2, 3, 4. So this alkene is tetrasubstituted. It's even more stable. So the most stable alkene is the thermodynamic product, which is this one. So the temperature is 100. So that's relatively high. Room temperature is like 20-25. So therefore, at high temperature, the thermodynamic product will be the major product. So therefore, this is the answer. So now what if the double bonds are not symmetrical? And let's use Br2 this time. So if they're not symmetrical, how would you draw all the possible products that can be produced? So keep in mind, we can count it both ways now. Let's count it from right to left. So let's say this is carbon 1, 2, 3, and 4. Let's draw the 1,4 product. So on carbon 1, we're going to put the first bromine atom. And for the 1,4 product, on carbon 4, we're going to put another bromine atom. And the double bond is going to be between 2 and 3. Now to draw the 1,2 product, on carbon 1, we're going to put a Br. And we're going to put a Br also on carbon 2. And the double bond is going to be between 3 and 4 for the 1,2 product. Now, let's say if we count it the other way. Let's make this carbon 1, 2, 3, and 4. So to draw the 1,4 product, the Br is going to be on carbon 1 and on carbon 4. And a double bond is going to be between 2 and 3. Notice that these two, it turns out, are identical to each other. So remember, you can get up to 4. Sometimes you can get 3. Now let's draw the 1,2 product. So the bromine atoms will be on carbons 1 and 2. And the double bond will be on between 3 and 4. Now these two are different. They're not the same. So here we have 3 different products. Now granted, if we were to use like HBr, these two might be different. But because the bromine atoms are the same, those two compounds are identical to each other. So let's say if the temperature, or if the reaction was carried out at negative 40 degrees Celsius, which one is going to be the major product? So let's analyze each one. So we're looking for the most stable carbocation intermediate. Now the carbocation is not going to be with the bromine on carbon 1. It's going to be with the bromine on carbon 4. So that's going to be this one here, which is secondary. And this one too, that's secondary. Well, that's carbon 1, so this is carbon 4. So that's primary. And carbon 2, this is secondary. So at low temperature, each one of these can form because the most stable carbocation is secondary. So therefore, we won't get this one at low temperature. Now, to see which one is better out of those, we need to find out which alkene is most stable. Now, this alkene is disubstituted. It has two R groups, 1, 2. Now, this one also has two R groups, 1, 2. But this one only has one R group, which is here. So this is monosubstituted. So under low temperature conditions, these two will be the major product. They have the highest or the most stable carbocation out of all the four that's listed, which is secondary, and they also have the most stable alkene. Now, under high temperature conditions, we can get this product because we have a disubstituted alkene. We can get this one or this one. This one's not going to happen because the alkene is not very stable. It's monosubstituted. So we won't get this at all. But under low temperature conditions, we're going to get just these two. So we get two different products. So that would be the kinetic product. So now it's your turn. Try this one. It's going to be in the ring this time. So let's say if we have a double bond here and here. And let's use HCl. So this time, let's count it this way. 1, 2, 3, 4. Let's draw the 1, 2 and the 1, 4 product. So hydrogen, which has the partial positive charge, is going to go on carbon 1. And chlorine, which has the partial negative charge, will go on carbons 2. And a double bond will remain between 3 and 4. So this is the 1, 2 addition product. And to draw the 1, 4 product, the hydrogen is going to remain on carbon 1. The double bond is going to be between 2 and 3. And chlorine is going to be on 4. So that's the 1, 4 product. Now let's count it the other way. So this time, let's say this is carbon 1, 2, 3, and 4. So hydrogen is going to go on carbon 1, and the Cl is going to go on carbon 2, and a double bond is going to be between 3 and 4 for the 1, 2 addition product. Now for the 1, 4, the hydrogen is going to remain on carbon 1. We're going to put the chlorine atom on carbon 4, and the double bond is going to be between 2 and 3. So that's the 1, 4 product. Now let's say if we heat it to 80 degrees Celsius, which one is the major product? So let's find out which is the most stable carbocation. So chlorine is more electronegative. That means it reacted with the carbocation. And here we have a secondary carbocation. This one is secondary. This one is secondary. But this one is tertiary. So automatically this is the kinetic product, which is the major product at low temperature. So now let's look for the thermodynamic product. So analyzing the two double bonded carbon atoms, we have 1, 2, 3 R groups. So this is tri-substituted. And for this one, let's see, we have 1, 2, 3 carbon atoms. So this also has 3 R groups. And for this one, there's 1, 2, so that's di-substituted. And then for the last one, we have 1, 2, 3, tri-substituted. So therefore, under high temperature conditions, we can get all three of these, because in terms of alkene stability, they're equally stable. So as you can see, the 1,4 products turned out to be thermodynamic products, but one of the 1,2 product was also a thermodynamic product in this case. However, one of the 1,2s was a kinetic. So the 1,2 is not always the kinetic. In this case it is, but this other 1,2 isn't. So the best way to ID, or to find out which one is going to be the thermodynamic product, is to find out which alkene is most stable. And for the kinetic product, you need to know which one passes through the most stable carbocation intermediate. So now what we're going to do is go through the mechanism for this reaction. So let's start with a symmetrical diene. So we're going to react with HBr. So the double bond, which is the nucleophile, is going to attack the hydrogen. And the electrons between the hydrogen and bromine atom are going to be pulled towards the bromine because bromine is more electronegative. And hydrogen is going to go on the primary carbon so that the plus charge will be on a more stable secondary carbon. And this carbocation is stabilized by resonance because this double bond can move over here. And so we can draw a resonance structure which looks like this. So now at this point, the bromide ion can react with any one of these carbocations. If it attacks here, we're going to get the 1,4 product. If it attacks here, the 1,2 product. And so that's how you can show the mechanism for this reaction. So now let's try a mechanism with an unsymmetrical system. So we can react any one of the two double bonds with HBr. So let's start with the first one, the one that's closest to us. So the hydrogen is going to go on one of these two carbon atoms, but it's going to go on the side that's furthest away to the other double bond, so that the plus charge could be right next to it. Now the reason for that is because if you put the plus charge one carbon away from the double bond, it's an allylic carbocation, and it's relatively stable. It's stabilized by resonance. And so just like before, this double bond can move here. And so the plus charge is here now. So then the bromide ion can attack this carbocation, or it can attack this one, giving us these two products. This is the 1,2 product, and we can also get the 1,4 product. So now let's react the other double bond with HBr. So this double bond can attack the hydrogen, and then the HBr bond is going to break. So we're going to put the hydrogen on a carbon that's away from the other double bond so that the plus charge can be next to it, and so resonance can occur. So after you draw your resonance structure, put the plus charge 2 carbons away from where the double bond came. And then at this point, the bromide ion could attack this carbocation, or it could attack the other one. And so that's how we're going to get the other two products. And that's it. So now let's move on into the Diels-Alder reaction. So The Diels-Alder reaction is a 4 plus 2 cycloaddition reaction. It's very useful for making 6 carbon rings. So on the left we have 1,3-butadiene, and on the right we have ethene. So here's the diene, and the other one is called the dienophile, the one that has one double bond. The diene, it works well if you add electron donating groups. It becomes more reactive. The dienophile works better if you add electron withdrawing groups. So it's a 4 plus 2 cycloaddition reaction because, as you can see, 1,3-butadiene has 4 carbons and ethene has 2 carbons. So it's going to form a 6-membered ring. Now, 1,3-butadiene can look like this, or it can look like this. This is called the S-trans form of 1,3-butadiene, and this is the S-cis form. For 1,3-butadiene to react in a Diels-Alder reaction, it has to adopt the S-cis conformation. So this is going to happen all at once. This double bond between 5 and 6 can form a connection between 1 and 6. The double bond between 1 and 2 is going to move between 2 and 3. And the double bond between 3 and 4 is going to connect 4 and 5. So out of the 3 double bonds, we're going to lose 2, and only 1 is going to remain. So we're going to have a 6-membered ring, and there's going to be a double bond left over between 2 and 3. So that's the Diels-Alder reaction. So let's try another example. Let's say if we have a diene with a methyl group. A methyl group is a weak electron donating group. Let's say if we have a dienophile with a very strong electron withdrawing group. What do you think the products will be for this reaction? So we're going to get a 6-membered ring, just like before. And the double bond is going to be between 2 and 3. So here's the methyl group, and here's the NO2 group. Now the NO2 could be in the front, or it can be in the back. Depends on how it approaches the dienophile, the diene. So we can get a mixture of products. We can get this one too. Now notice that I didn't put the CH3 in the front or in the back. The carbon that has the CH3 is not chiral because of the double bond. This carbon only has 3 different groups. For it to be chiral, it has to have 4 different groups. But the carbon with the NO2 does have 4 different groups. There is an invisible hydrogen that is now visible. And the NO2, instead of being in the front, it can be in the back. So you can get the enantiomer as well. So here's a mixture of stereoisomers. Now, we can get more than 2 stereoisomers though. We can get more than 2 products. So the dienophile can approach the diene in the opposite way, so to speak, with the NO2 facing away from the methyl group. And if that happens, it's possible that we can get a different product. So we can get this product instead. And we can also get the enantiomer, where instead of putting the NO2 on the wedge, we can put it on a dash. So we can get up to 4 different products as this example illustrated. Try this one. So this time, let's use a methoxy group, which is a relatively strong electron donating group because of the lone pairs that it has. And this time, on a dienophile, we're going to have 2 powerful electron withdrawing groups. So what do you think the major product for this reaction is? So we're going to get the 6-membered ring with the double bond being on carbon 2. And we're still going to have the methoxy group, and it's the same position. But notice that we have 2 carboxylic acids, and they're cis with respect to each other, which means that they're going to have to be on the same side. They can be like this, both on the wedge, or we could draw it the other way. where they're both on the dash. And so we can draw it like this. So here we can get two different products. Now, if this methoxy group wasn't there, we would have symmetry. And so we would have a meso product, which it won't be two products, it will be one, if the methoxy group wasn't there. So now let's try another example. The best way to learn is by working through a series of examples. Try this one. Go ahead and draw the major product for this reaction. So we can call this carbon 1, 2, 3, 4, 5, 6. So we're still going to get the 6-membered ring. And the double bond is going to be between 2 and 3. Now on 1 and 4 we do have a methyl group. And on 5 and 6 we have two NO2 groups trans with respect to each other. So one will be in the front and the other will be in the back. And plus we can get the enantiomer. Try this one. Let's say if the dienophile has a triple bond. What are you going to do now? So the triple bond is going to become or turn into a double bond. And so we're still going to get the same 6-carbon structure. And it's going to be a double bond between carbons 2 and 3. But the triple is going to be reduced to a double, so it's going to be between 5 and 6. And we have the two CF3 groups. Now what you need to keep in mind is that because we have a ring and a double bond, these two carbon atoms are not chiral, so there's no cis or trans systems, and we don't have to worry about enantiomers and meso compounds and things like that, since we don't have a chiral center. However, we do have a chiral center here, so I mean that's pretty significant. So therefore this methyl group can be in the front, and it's possible that it can be in the back too as well, since it's chiral, so we can also get the enantiomer. But these two carbons are not chiral, so there's no chirality at those carbons. Now let's say if you were to get a reaction that looks like this. What do you think the product for this reaction is? Now, what I would do is redraw the system. Let's call this carbon 1, 2, 3, and 4. Notice the 1,3-butadiene system that we have, in addition to the extra methyl group. It's really 5 carbons, but I would focus on this 4-carbon system. So on carbon 1, we have a methyl group. So let's call this 1, 2, 3, 4. And let's call this 5 and 6. That's going to be the dienophile part of this molecule. And notice that it's in the S trans form, which means that the carboxylic acids are trans with respect to each other. So this is really what we have. So now we could draw the product. So we know we're going to get a 6-carbon ring as always. And we have a methyl group on carbon 1. And the carboxylic acids are trans with respect to each other. So it's going to look like this. And plus, we can get the enantiomer for that particular compound. So sometimes you might get a Diels-Alder reaction, but it may not look like it. So you may have to restructure the problem. Draw it in a way that is most familiar to you. Now, what if we had a cyclopentadiene, which looks like this. And if we mix it with a dienophile, what do you think the products for this reaction will be? So this is going to be carbon 1, 2, 3, and 4, and here's 5 and 6. Now we're still going to get a 6-membered ring, but since we started with a ring, we're going to have 2 rings. So we're going to have a bicyclic system. So we're going to draw it differently. Let's draw our 6 carbon structure like this. And notice that we have this carbon here. Let's call it carbon A. Carbon A is over here. And so this is carbon 1, 2, 3, 4, 5, 6. Between 2 and 3, we still have a double bond. And on 5 and 6, we have 2 NO2 groups. Because they're cis with respect to each other, we can put them facing outward, like this. This is called the exo product, which is not the major product, it's the minor product. And then there's the endo product, which looks like this, with the NO2s facing in a downward direction. It turns out that the endo product is the major product. So you're going to get this. This should be your answer. On a test, that's what you're looking for. By the way, sometimes you might see the answer. It might look like this. So instead of drawing it this way, you might see the answer like this. Here's that extra carbon, and a double bond is between 2 and 3. And the NO2 groups, they could be cis with respect to each other. Well, they have to be cis. So you might see it like this, but the only problem with this representation is you don't know if it's in the endo or exo form. So this is the better way to present it, but you might see the answer like this too. Now let's try another example. So let's say if we have a 1,3 cyclo, instead of cyclopentadiene, let's say if we have 1,3 cyclohexadiene, and let's react it with this particular compound. So go ahead and draw the major product. So this is going to be carbon 1, 2, 3, 4, 5, and 6. So here is our 6 carbon structure. And notice that there's 2 carbons between 4 and 1. So we're going to draw it like this time. We're still going to have a double bond between 2 and 3. Now notice that we have a trans system. That means one of the electron withdrawn groups is going to be in the exo position and the other is going to be in the endo position. So we can also draw it this way. Because one is endo and the other is in the exo position, these 2 products are equally stable. So you can get both. So try this example. See if you can get the answer for this one. So this is going to be carbon 1, 2, 3, 4, 5, and 6. So let's draw our 6-membered structure. So between 1 and 4, we have an oxygen atom, which we're going to put on top. And there's a double bond between 2 and 3. And notice that we have a triple bond for the dienophile, so therefore it's going to be reduced to a double bond. And because we have a double bond and a ring at these 2 carbon atoms, endo and exo really doesn't apply. So we could just draw 2 NO2 groups sideways. And so that is going to be the answer. Now, what about this example? Let's say if you have something that looks like this. what do you think the major product is going to be? So notice that we have like a double Diels-Alder reaction on the left and right side. So this is the diene for the dienophile for the left side, and this is the dienophile from the right side. So here we're going to have a Diels-Alder reaction, and we're also going to have another one here as well. So we're going to create two additional rings. And we're going to have a double bond on these two sides, and that's about it. So this is the product for this reaction. So now what if you're given the product? How can you draw the diene and the dienophile that was used to create this particular product? How would you deconstruct it? So the first thing I would do is make sure that this double bond is between 2 and 3. And then draw your generic diene, which always going to look like this, and your dienophile. So on carbons, we know the diene, the double bond is going to be between carbons 1 and 2 and 3 and 4. That's just the way it is. And we can see on 6 we have an NO2 group. So this is the diene that was used to make it, and here is the dienophile. So you just got to work backwards. But let's try a few examples working backwards. So now it's your turn. Let's say if you have this particular compound, draw the diene and the dienophile that was used to make this product. So this double bond has to be between 2 and 3. So this would be 1 and 4, and here's 5 and 6. So I'm going to draw the same type of diene that I've been using. So there's nothing special between carbons 1 and 4, or 1, 2, 3, 4. And on 5 and 6, we're going to have two CF3 groups, but notice that they're trans with respect to each other. So one is going to point towards the right, and the other is going to point towards the left. And so that's the diene and the dienophile that was used to make this product. Try this one. So identify the diene and the dienophile that made this particular product. So this is carbon 1, 2, 3, and 4. So we're going to draw the generic diene, and we have a methoxy group on carbon 2. And for the dienophile, the NO2 groups have to be cis with respect to each other, so they're going to be on the same side. Now, what about for this bicyclic system? Draw the diene and the dienophile that was used to make it. So we need to know that this is carbon 1, 2, 3, and 4, and this is 5 and 6. So, but notice that we also have these two carbons. So here's the first 4 carbon atoms. On 2 and 3 we have a methyl group. Now attached to a carbon 1 and 2 we have 2 other carbons, which are these 2 carbon atoms. So that's the diene. And for the dienophile, these two groups are on the same side. They're in the endo position, so we know it came from a cis alkene. And so now you know how to identify the diene and the dienophile that makes up that product. So that is it for the Diels-Alder reaction. So now let's move on to our next topic. So let's jump into benzene reactions, specifically electrophilic aromatic substitution reactions. So here's benzene. It's aromatic, very stable. And I'm going to draw two hydrogen atoms. Now each carbon atom has at least one hydrogen atom. And we're going to react it with an electrophile. So let's go over the mechanism for the electrophilic aromatic substitution reactions, which I'll refer to as EAS reactions. So in the first step, the double bond is going to attack the electrophile. So the first step is an addition step because we're adding the electrophile. So let's add it to this carbon. If we add it to this carbon, that means the plus charge is on the adjacent carbon. And we still have these double bonds, so the plus charge can delocalize into the ring. But we have this relatively unstable carbocation intermediate. Now, in the next step, one of the hydrogen atoms is going to leave. So let's use a generic weak base. Well, I'm just going to put B with a lone pair. So the base will grab a hydrogen, and then the carbon-hydrogen bond is going to break those electrons that are going to be used to regenerate the double bond that was lost. So the second step is an elimination step. When you combine addition and elimination, addition and elimination equals substitution overall. So this is our final product. So overall, what we did is we replaced a hydrogen with an electrophile. So that's why it's called an electrophilic substitution reaction, because we're substituting a hydrogen with an electrophile. And because this reaction is associated with aromatic rings, it's called an electrophilic aromatic substitution reaction. The energy diagram for such a reaction looks like this. This reaction occurred in two steps. So there should be like two heels, so to speak. This is the first transition state, and this is the second one. Here we have the reactants, the products, and the intermediate. Notice that the intermediate is higher in energy than the reactants and the products because carbocation intermediates are relatively unstable compared to something that doesn't have a plus charge. So this intermediate is usually higher than the reactants or the products. The next thing you need to know is something called ortho-para directors. Now let's say if we have a nitro group, and let's call this carbon 1, and this is 2, 3, 4. You need to know that 1, 2 is ortho, 1, 3 is meta, and 1, 4 is para. So the nitro group is a meta director, which means that it directs an electrophile to position 3. Ortho-para directors would direct the electrophile to go to carbons 2 and 4. So now you need to know which groups are ortho-para directors and which ones are meta directors. So let's start with ortho-para directors. Some ortho-para directors are pretty strong. So like NH2 and OH, these are some relatively strong ortho-para directors. So these are strong activators. Now notice that the first atom that's attached to the benzene ring has a lone pair, and also it's electronegative, meaning that it has a partial negative charge. These are ortho-para directors. They can donate electron density to the ring by means of the resonance effect. Now, so these are strong activators. I'm going to write SA for strong activators. Now, we have some other ones known as moderately activating groups. The Carbonyl group, it weakens the lone pair on the NH because this lone pair can delocalize into the benzene ring, but it can also be pulled by the Carbonyl group. And so it's a weaker activator. It's a moderate activator, but it's weaker than these two because they're strongly activating. A group that is strongly activating makes the ring more reactive towards EAS reactions. So this one too, it's also a moderately activating group. So I'm going to write MA for moderately activating. And then you have like R groups like CH3, an aromatic ring. These are weakly activating. Now this nitrogen is electronegative. It has a partial negative charge. The same is true for oxygen. Now let's analyze the CH3 group. Now the CH3 group doesn't have any lone pairs, but it turns out that carbon is more electronegative than hydrogen. So carbon has a partial negative charge and hydrogen has a partial positive charge. The electronegativity value for carbon is 2.5, but for hydrogen is 2.1. So because the first atom has a partial negative charge, overall it's an orthopair director. And so that's just what it is. It's a weak activator, but it's still orthopair directing. And there was something else I wanted to mention. Carbon donates electron density to the ring by means of the inductive effect. It doesn't have any lone pairs, so it can't really donate electron density by means of the resonance effect. Now the next group are the halogens, like fluorine, chlorine, bromine, and iodine. Let's analyze fluorine. Now fluorine is electronegative, so it bears a partial negative charge. And like everything else, like the CH3, the OH, the NH2, because it has that partial negative charge, it's still an orthopair director. And also, fluorine, which has a lone pair, can donate electron density to the ring by means of the resonance effect. But fluorine's electronegative, which means it can pull electrons toward itself by means of the inductive effect. Now, it turns out that the inductive effect for the halogens exceed their electron donating effect. Their electron withdrawn effect by means of the inductive effect is stronger than their electron donating capabilities which occur by means of the resonance effect. So therefore, the halogens are weakly deactivating. So they make the ring slightly less reactive towards EAS reactions. But even though they're weakly deactivating groups, they are still orthopair directing. So make sure you are aware of that fact. So now let's talk about the meta directors. The meta directors are very strong electron withdrawn groups. And some of the most common examples include the carbonyl groups, like the aldehyde, the ester, and even the carboxylic acid. In each of these cases, notice that the first atom, the carbon atom, has a partial positive charge because each and every one of them are attached to very electronegative atoms like this carbonyl group, which withdraws electron density away from the carbon, making it partially positive. And the oxygen is partially negative. So these are the moderately deactivating groups. So I'm going to write MDA for moderately deactivating. And then you have like some strongly deactivating groups. This includes like the nitro group, the NO2, which I'm going to draw it like this. You have SO3H, and you have CF3, NH3, and CN. The nitro group is one of the most powerful electron withdrawing groups. The nitrogen has a positive formal charge, and it's also partially positive as well because it's attached to two electronegative oxygen atoms, which bears a partial negative charge. Now the same is true for sulfur. It's partially positive, and this carbon is partially positive. It's attached to three electronegative fluorine atoms. Now this nitrogen, NH3, has a positive formal charge, and this carbon also has a partial positive charge. So as you can see, whenever the first atom has a partial positive charge, it's usually a meta director. And if the first atom has a partial negative charge, it's usually an ortho pair director. And just looking at that one difference can help you to find out what type of director you have. Now, the groups on the bottom are strongly deactivating. So a strongly deactivating group makes the benzene ring less reactive. Now, starting with benzene, what's going to happen if we react it with nitric acid and sulfuric acid? In this reaction, a hydrogen is going to be replaced with an NO2 group. It's an electrophilic aromatic substitution reaction. Now make sure you know the intermediate of this reaction. The intermediate is the nitronium ion species, which looks like this. So that's NO2 plus. That's the electrophile that reacts with the benzene ring. So the first step is easy. All you got to do is put a nitro group on a benzene ring. Now what's going to happen, oh by the way, the first reaction is called nitration. I'll make sure you know the name as well. Now what's going to happen if we add, let's say Br2 with FeBr3. FeBr3, iron 3 bromide, that's the Lewis acid catalyst. It helps the reaction to proceed. Without it, it won't work. Now, NO2 is a meta-director. So if the nitro group is on carbon 1, it's going to direct the bromine to go on carbon 3, which could be this side or over here as well. If you count, actually no, that's too far. Or over here, if you count it the other way. But those two positions are identical, so it doesn't matter which one we use. So let's use the one on the bottom. So this is going to be the product for this reaction. Now what's going to happen if we take this product and add sulfur trioxide with sulfuric acid? By the way, the last reaction is called bromination, by the way. Now this reaction is called sulfonation. Now the nitro group, which is the meta-director, wants the SO3 to go here, but bromine is an ortho pair director, and it wants it to go to the ortho position, which is 1,2 with respect to bromine, or the para position, which is 1,4 with respect to the bromine atom. One of the arrows that we can eliminate is this one. It's going to be very difficult for it to approach this side because there's two groups on this side, and they're going to create some sort of steric hindrance. They're going to sort of block the SO3 from approaching that direction. It can still happen, but it's just less likely to occur. Now, which group is more activating, the bromine atom or the nitro group? The nitro group is a strongly deactivator. It's a very strong deactivator. But the bromine atom is a weak deactivator. So therefore, it's more activating than the NO2 group. So SO3 is most likely going to listen to the bromine atom rather than the NO2 group. So it can go here or here. So we can get both products, but I'm just going to draw one. So this is one of the products that we can get. Now what's going to happen if I add H3O plus or just water, just boiling water? If you add boiling water, desulfonation can occur. So this reaction will go back this way. The SO3 will leave as SO3 gas if you boil it in water. So that's how you can remove an SO3 group if you need to. Now, starting with benzene, what's going to happen if we add a Cl2 with FeCl3? So this reaction is called chlorination. And all we got to do is just add a chlorine to the benzene ring. Now, what if we add nitric acid and sulfuric acid to this product? What's going to happen? So this is nitration, and chlorine is an ortho pair director. So it can direct it to the second position or the fourth position. So the NO2 can go here, or it can go here. So let's draw the ortho product first. Keep in mind, we can get a mixture of both the ortho and the para product. But let's start with the ortho product. If we add iodine with nitric acid, what's going to happen? Now, nitric acid is going to act as an oxidizing agent, and it's going to oxidize the I2, or it's going to take electrons away from it, so we can get the I plus electrophile. Basically, the overall process for this reaction is that we're going to add the iodine to the ring. The question is, where is it going to go? Now, chlorine is an ortho para director. It wants the iodine to go to the ortho position or the para position. NO2 is a meta director, so it wants it to go to the meta position. Now, both of these groups, they're pointing in the same direction. Now, this position is a little bit better than this one because this one is closer to the chlorine, and so there might be some steric factors that you have to take into account. So let's draw the para product, the one that's para with respect to chlorine. So it's going to be slightly better than the ortho product because it's further away from the chlorine. But you can still get both products though. So you do get a mixture, but we're going to draw the para product. The yield should be slightly better. Now, let's go backwards. Let's say if we drew the other product after nitration. So let's say if the NO2 group went in the para position. What's going to happen once we add I2 with nitric acid? Where is the iodine going to go now? So chlorine is an ortho para director, so it can direct to the ortho position. These two positions are the same because they're one away from the chlorine atom and they're both two away from the nitro group. So we don't have to worry about the other side. Now the NO2 is a meta director, so meta is 1, 3 with respect to the NO2 group, so it wants it to go here as well. So both of these groups, they favor the formation of the same product. So therefore, these two, they don't compete against each other, they work together. So the iodine is definitely going to go here. Now, starting with benzene, what's going to happen if we add methyl chloride with the aluminum chloride catalyst? This is the Friedel-Crafts alkylation reaction. And so the catalyst is going to take away the chlorine, and you're going to get a methyl cation, which this can't rearrange. And the benzene ring is going to attack the methyl group. And so the net result is that we're going to replace a hydrogen with a methyl group. And so you get this product. Now, something you have to keep in mind is that the Friedel-Crafts alkylation reaction is susceptible. I said that word wrong. It's susceptible to rearrangements. So you got to watch out for rearrangements, and also you need to know that the Friedel-Crafts alkylation reaction, it doesn't work very well if the ring is heavily deactivated. So if you have a nitro group on a ring, the Friedel-Crafts alkylation reaction doesn't work very well with that. So let's say if we add ethyl chloride with aluminum chloride. This won't rearrange because both carbon atoms are primary. If there was a secondary carbon, then it might rearrange. Now the methyl group is a weakly deactivating ortho para director. So the ethyl group can go here or here. But let's draw the ortho product. So here's the methyl and here's the ethyl. Now what if we add tert-butyl chloride? Notice that the chlorine is on the most substituted tertiary carbon. So tert-butyl chloride won't rearrange. Now the methyl group wants it to go to the ortho or the para position, and the ethyl group wants it to go to the ortho or pair position. So tert-butyl chloride can go anywhere. But because it's so bulky, it doesn't really want to go next to the methyl or the ethyl group. So we're going to take away these two positions. And we'll just pick one. So let's just pick this side, because we can get a mixture at this point. So what we now have is something that looks like this. There's our tert-butyl group. Here's our methyl and our ethyl group. Now what's going to happen at this point if we use potassium permanganate and H3O+? At this point we're going to get a side chain oxidation reaction. So this is going to oxidize the carbon atoms outside of the benzene ring if there's a benzylic hydrogen. So there's hydrogens on this carbon, we have hydrogens on this carbon, but this carbon is quaternary, it doesn't have any hydrogens on it. So therefore the tert-butyl group is not susceptible to oxidation. So potassium permanganate will not oxidize it. It's going to stay the same. So you're going to have this. The tert-butyl group is going to remain. Now, the methyl group is going to be oxidized to a carboxylic acid. And the ethyl group will also be oxidized to a carboxylic acid. And it doesn't matter how many carbon atoms are here. If you had a butyl group, it would still be oxidized to a carboxylic acid. Now, what's going to happen if we have benzene and if we react it with propyl chloride and the aluminum chloride catalyst? What's going to be the major product for this reaction? Now, this is the Friedel-Crafts alkylation reaction, and notice that the carbon that has the chlorine is a primary carbon, but there's a secondary carbon adjacent to it. So this reaction is going to have a rearrangement, a carbocation rearrangement, and so the product is going to look like this. We're going to get isopropyl benzene, and we're not going to get propyl benzene. So you won't get this product. It's not going to be like that. Now let's understand why and how it happens. So we need to go through the mechanism for this reaction. Now the first thing that happens is the alkyl halide, it reacts with the Lewis acid catalyst. So the chlorine, it binds with the aluminum. And so we're going to get this adduct. When aluminum has 4 bonds, it has a negative formal charge. And when chlorine has 2 bonds, it's going to have a positive formal charge. So now the bond between the carbon and the chlorine is going to break, and because chlorine is more electronegative, the chlorine atom is going to take those 2 electrons in that bond. And so what we now have is a primary carbocation, and somewhere in this side we have AlCl4-. Now primary carbocations are not very stable, and so a hydride shift is going to occur. So this hydride is going to move here, and we're going to get a secondary carbocation. Now, because primary carbocations are difficult to form, another way you can show the mechanism for this step is by skipping the formation of an unstable carbocation intermediate. So you can also do this. You can draw the hydride shift before forming the carbocation. So this hydride could attack this carbon and force in this bond to break, pushing those electrons back to the chlorine. And the net effect is you're still going to get the same secondary carbocation intermediate. And once we have that secondary carbocation, now it can react with the benzene ring. And so this is our electrophile. So the double bond is going to react with the electrophile, and we're going to get a carbocation intermediate on the benzene ring. So now we have a plus charge on this carbon. And so at this point, we can use the chloride ion to remove the hydrogen. AlCl4 minus is in equilibrium with AlCl3 and Cl minus. So let's use the chloride ion as a weak base. So this can take away the hydrogen, and the electrons in the carbon-hydrogen bond is going to be used to regenerate the double bond. So keep in mind, for this electrophilic aromatic substitution reaction, the first step is an addition step because we added the isopropyl carbocation to it. And then the second step was an elimination step because we eliminated or removed the hydrogen. So overall, this is a substitution reaction, and specifically an electrophilic aromatic substitution reaction. Notice that for EAS reactions, a plus charge is going to be on the ring. You're going to have an intermediate that's going to have a plus charge. For some nucleophilic aromatic substitution reactions, a negative charge can be placed on the ring, specifically the one that is associated with the Meisenheimer complex, which we'll talk about later. There's three kinds of reactions that you need to be familiar with. This one, the EAS reaction, and there's two types of nucleophilic aromatic substitution reaction. One that occurs through the benzene intermediate, and the other that occurs through the Meisenheimer complex. But for now, this is the answer for this particular reaction. So then, if using isopropyl chloride rearranges to give us isopropyl benzene, how can we make propylbenzene from benzene? How can we get this product and not this one? So what do we need to do here? Any suggestions? So we need to use the Friedel-Crafts acylation reaction. So we need an acid chloride with 3 carbons, and we need the aluminum chloride catalyst. Let me put this over here. So what's going to happen is we're going to get a ketone. The chlorine is going to leave, and the benzene ring is going to attach itself to this group. And we'll go over the mechanism for that process soon. And now to get this product, you simply need to use the Clemmensen reduction, which is zinc with mercury and HCl. It's going to reduce the ketone into an alkane. You can also use the Wolff-Kishner reduction reaction, which it has hydrazine N2H4 with a strong base, potassium hydroxide. That's the Wolff-Kishner reduction, and it does the same thing as the Clemmensen reduction. Now sometimes you might see hydrazine in this form as H2N and H2. It's the same as N2H4. Now let's go over the mechanism for that process. So, starting with the acid chloride, this is going to react with the aluminum chloride catalyst. And so, these two will combine. And the chlorine is going to have a plus charge, and the aluminum is going to have a negative formal charge. And then chlorine is going to take away these 2 electrons. And so what we now have is a carbon with a plus charge. And AlCl4 minus is somewhere in the solution. Now, this cation is stabilized by the oxygen. The oxygen can use one of its lone pairs to form a triple bond. And so what we have now is something called an acylinium ion. And that's the intermediate for this reaction. By the way, between these two resonance forms, which one is the major resonance contributor? Which of these two resonance forms is more stable? Is it the one on the left or the one on the right? What would you say? So here's the question: is it better to put a positive charge on a carbon atom or on the oxygen atom? If it's a positive or negative charge, it's more stable if you put it on the oxygen atom. So this is the major resonance contributor. So now we can use benzene to react it with either one of these two resonance forms. But let's react it with the major resonance form. So here's benzene, and here is our acylinium ion. So the double bond is going to attack the carbon, and one of the pi bonds has to break, and oxygen is going to pull those electrons toward itself. And so at this point, what we have is this structure. So now we have a double bond instead of a triple bond. And we still have the two additional carbons on the right. So there's a hydrogen here, and there's another hydrogen here, which means that there's a plus charge on this carbon. So now we're going to use the chloride ion as a weak base to remove this hydrogen. And then these electrons will be used to form a double bond. And so now we have our final answer. So as you can see, once you get the electrophile, the mechanism is identical to the other reactions. But you just need to know how to get the electrophile. And so this is it. So now that you know the generic reaction, let's talk about how to get the electrophiles for the other reactions. Let's go over the mechanism for the nitration of benzene. So we know that the first thing we need to do is combine nitric acid with sulfuric acid to generate the electrophile. Now, nitric acid is going to look like this. We're going to have an OH on one side and an oxygen with a negative charge. Now, nitrogen has a positive formal charge, so overall, the net charge is 0. So that's why HNO3 is neutral, but it has formal charges within its structure. So now this is going to react with sulfuric acid, and sulfuric acid is a strong acid. It's very easy to remove the first proton. And so this oxygen is going to grab a hydrogen from sulfuric acid. And whenever an OH grabs the hydrogen, you get H2O, and it turns into a good lever group. So there's H2O. And since H2SO4 lost a hydrogen, it's now in the form as HSO4-. It's somewhere in the solution. Now, this oxygen also has a plus charge, which makes it a good leaving group. So this oxygen on the left is going to use its lone pair to form a double bond, and it's going to expel H2O. And so this is the nitronium ion species. As you can see, the nitrogen has a positive formal charge. And benzene is going to react with the NO2 group. And so here's what's going to happen. So the double bond is going to attack the nitrogen, and one of the pi bonds is going to break. It doesn't matter which one. So keep in mind, there's a hydrogen on this carbon, and there's another one on that carbon. So now we have NO2, which looks like this. And we have a hydrogen here and here as well. and there's a plus charge on this carbon. So now we can use HSO4- as a weak base, or we can use water because we expelled water in the last step. So let's use water as a weak base. So H2O can grab a hydrogen, and then the carbon-hydrogen bond is going to break, as always. And so now we have our product, which we can write it like this. So that's the mechanism for the nitration of benzene. That's how you can write the mechanism. So now, let's talk about the sulfonation mechanism. So sulfuric acid can react with itself or another sulfuric acid molecule. So one of the oxygens is going to be protonated by the other acid. And once you get water, it's a good leaving group. So this oxygen is going to form a double bond and expel H2O. And so this is going to be the reactive species. So this oxygen has a positive formal charge. But the sulfur is highly electropositive because it's attached to 3 electronegative oxygen atoms. Keep in mind, formal charge and partial charge are different. They're not the same thing. So it's really SO3 that is the electrophile. And sometimes the SO3 group can be protonated because this reaction occurs under acidic conditions. So we can react benzene with SO3 or SO3H. But let's use SO3. Let's use a deprotonated form. So the double bond is going to attack the sulfur atom, and one of the pi bonds is going to break. And so we're going to have this. And then we can use water to take away this hydrogen. And so we're going to get this answer. Now, this oxygen with a negative charge can easily pick up a hydrogen ion in a solution because the solution is highly acidic. And so the end result is that we're going to have SO3H. But what you need to know for this reaction is this is the electrophile, because sometimes you might get tested on which electrophile is the attacking species of a certain reaction. And to understand that, you need to know the mechanism of that reaction. Now let's move on to a different topic. So let's say if we have nitrobenzene, what's going to happen if we add iron metal with hydrochloric acid? Now we can add any active metal. It can be zinc with hydrochloric acid or even a tin metal with hydrochloric acid. This is going to be a reduction reaction. The nitro group is going to be reduced into an NH2 group. So this is one way you can make aniline. A benzene ring with an NH2 group is called aniline. You need to be familiar with some parent names for benzene derivatives. Now, what's going to happen if we add sodium nitrite with hydrochloric acid at very low temperature conditions, like 5 degrees Celsius? Sometimes you might see it as HNO2, or you might see it as HONO, which is the same as HNO2. Any NO2 with HCl produces HNO2 and NaCl. So this step can be written any one of these 3 ways. It's going to lead to the same product. So what's going to happen is the N2 group the NH2 group is going to be converted into an N2 group. And so you're going to get something that looks like this. It's called an arene diazonium salt. Now, from this reaction, there's a lot of things you can do. You can add copper bromide, and it's going to replace the N2 group with a bromine atom. So you're going to get a bromobenzene. Or you can add copper chloride, CuCl, and you can get chlorobenzene instead. Or you can add copper cyanide, CuCN, and get a nitrile group instead. The reactions that are using the copper 1 cation, these reactions with the arene diazonium salt are known as the sand-mine reactions. So here we're going to get a nitrile group. Now, let's say if we were to use copper oxide with H2O, we can replace the N2 group with an OH group. So this is one way you can make phenol, which is another name that you need to be familiar with. And if we use fluoroboric acid, HbF4, we can replace it with a fluorine group. And so that's one way you can put a fluorine atom on a benzene ring. And finally, if we add H3PO2, we can replace it with a hydrogen. So this is one useful way in which you can get rid of a nitro group and go back to benzene. So now let's move on from, well, actually there's one more reaction that we need to go over regarding electrophilic aromatic substitution reactions. And before I forget, it's this one. Let's say if we have phenol, and if we react it with an arene diazonium salt. So these two, they can combine and they can basically form one single product. So phenol is a very nucleophilic benzene molecule. It's activated by the OH group. And so this OH group can donate electron density to the ring. And so it's going to cause this double bond to move here, which will cause this double bond to attack the nitrogen atom, which will cause this triple bond to push a pair of electrons on this nitrogen. And so these two are going to combine, and they're going to form like an azide linkage. This reaction is very useful for making azo dyes. Notice that the system is conjugated. And whenever you have very extensive conjugated systems, they tend to exhibit a variety of color. Like think of beta carotene, which is found in which is found in carrots. It has that orange color to it. Beta carotene has a lot of conjugated double bonds. At this point, the oxygen now bears the positive charge, and these two nitrogens have a lone pair. Now don't forget, there was a hydrogen on this carbon, so we need to get rid of that hydrogen. So let's use the chloride to do that for us. So the chloride can act as a weak base, grabbing the hydrogen, causing the carbon-hydrogen bond to break, pushing those electrons back here. And those electrons are going to move towards the oxygen, which has a positive formal charge. And so now what we have is our final product, which looks like this. And so that's the answer. So just keep in mind that these can happen. And the OH group is an ortho pair director. And typically when you have like whenever you're going to form an azide linkage, it usually goes in a pair position. So just make sure you're aware of that. Now before we move on to nucleophilic aromatic substitution reactions, there's something else I do need to quiz you on before I forget. Let's say if you have 2 benzene rings instead of 1, and let's say if we wish to react it with Br2 and FeBr3. So first question, which ring is going to react with the bromine atom? And where on that ring is the bromine atom going to go? So we need to know which ring is activated and which one is deactivated. So here's a quick way to tell. This carbon has a partial positive charge, and the oxygen has a partial negative charge. So the ring on the left, the electrons in that ring are being pulled towards the carbonyl group, and so therefore the ring on the left side is deactivated. The carbonyl group is a moderate deactivator. Now the oxygen, which is partially negative, can donate electron density to the ring on the right. It can donate by means of the resonance effect. So because it can donate electron density, the ring on the right side is activated towards EAS reactions. And so the bromine is going to react with the ring on the right side. So now the oxygen, which has a partial negative charge, we know it's an ortho pair director. The carbon with the partial positive charge is a meta director. Ortho pair directors, at least most of them, are usually activators. And so the bromine, it can go on the ortho position or on a para position. If you have to choose, pick the para position. So the answer for this reaction is going to be this product right here. So this is the answer, because the ring on the right is more activated or more reactive than the ring on the left. So now let's talk about nucleophilic aromatic substitution reactions. So everything is opposite for this particular reaction. For electrophilic aromatic substitution reactions, groups like OH and NH2, those were activating groups. They activate the ring towards electrophilic aromatic substitution reactions. But now for nucleophilic aromatic substitution reactions, electron withdrawing groups like the nitro group can activate the ring towards an NAS reaction. Now in the nucleophilic aromatic substitution reaction, we're going to replace not a hydrogen but a halogen with a nucleophile. So in this particular reaction, the nucleophile is NH2 minus. And so we're going to replace the bromine atom with it. And so this is going to be the product. So this is one example of a nucleophilic aromatic substitution reaction. But this one is specifically the one that goes through the benzene intermediate. But let's write the mechanism for this reaction. Now the benzene intermediate reaction is not an addition-elimination reaction, it's elimination-addition. So the first thing that happens is NH2 minus, it acts as a base, and it's going to grab a hydrogen. And then the carbon-hydrogen bond is going to break. Those electrons will be used to form a triple bond, and the Br will be expelled. So as you can see, the first step is an elimination step because we removed hydrogen and Br from the ring. And so we get an intermediate called benzene, which it looks like benzene, but there's a triple bond. Whenever you have an alkyne, you have a triple bond, so we call it benzene. Now at this point, the NH2 minus ion is going to act as a nucleophile. It's going to attack the carbon. Now, it can attack the carbon from the left side, or it can attack it from the right side. I mean, that's the left side, but before it was the right side. So let's say it attacks it from the right side. If it does, then it's going to push 2 electrons on this carbon. So we now have this structure. So the NH2 is on the benzene ring, and we have a lone pair. So the second step is an addition step, because we added NH2. So now the carbon with the lone pair is going to grab a hydrogen from NH3. And so now the reaction is complete. So the end result is that we replace the bromine atom with an NH2 group. Now keep in mind the triple bond can form on the right side, or it can form on the left side of the bromine atom. So therefore the NH2, it can go on any one of these 3 carbon atoms. So sometimes you might get 1 product, you might get 2, or you may even get 3 products. In this case, we only got 1 product because there was no other substituents around. Now, let's say if we had para-bromotoluene. When you have a CH3 on the benzene ring, it's called toluene if that's part of the parent name. So now let's say if we use a sodium amide. Draw all the possible products for this reaction. So the NH2 can go on the carbon that has the bromine atom, or it can go 1 carbon to the right or to the left. Notice that these 2 positions are identical if we put the NH2 there, so we only get 2 different products. For the first one, we can replace the Br with the NH2 group. And so now the parent name is aniline, so we can get para-methyl-aniline, or we can get meta-methyl-aniline. So the NH2 group could be on this side. So we can get 2 different products. Now, let's put the methyl group meta with respect to the Br. And let's add NH2. The NH2 can go on the carbon that has the Br. It can go 1 carbon to the left or 1 carbon to the right. And so we can put it here. This is going to be 1 product. Or we can put it on the left side, and so that's going to be a different product. And we can also put it on the right side. And so all 3 of these products are different. So this is the ortho product, this is the meta product, and this is the para product. So this is one example in which we can get 3 different products with the benzene intermediate reaction. Now, it turns out that there's another nucleophilic aromatic substitution reaction. And typically, this is the one that goes through the Meisenheimer complex. And for this to work, you usually need like a very powerful electron withdrawn group, like a nitro group. And so we can use a weaker nucleophile like sodium hydroxide to make this work. Now we might need to add some heat to it to speed it up, but hydroxide is going to be the nucleophile. And instead of replacing a hydrogen like we did in an EAS reaction, in this nucleophilic aromatic substitution reaction, we're going to replace a halogen with a nucleophile. And that's how you could distinguish the two. If you're replacing a hydrogen atom, it's an EAS reaction. If you're replacing a halogen, it's an NAS reaction. So the end result is that we're going to get this product. We're going to replace the Cl with an OH group. But now let's work through the mechanism for that reaction. So the first thing that's going to happen is hydroxide is going to attack the carbon that has the chlorine. Chlorine is electronegative with respect to carbon, so the chlorine atom bears a partial negative charge. Now the carbon atom that is attached to the chlorine has a partial positive charge, which the hydroxide ion is attracted to. So hydroxide is going to attack this carbon. And it's not going to just kick out the Cl immediately. That's not going to happen. So what's going to happen next then is this double bond is going to move towards the nitro group, causing this double bond to move here, causing this pi bond to break. So as hydroxide attacks the carbon with the chlorine, the electrons are flowing towards the nitro group because the nitro group is an electron withdrawn group. So the nitro group helps pull the electron density towards itself. And so we're going to get this intermediate. So now we need to get rid of the Cl. So one of the oxygens with a negative charge, it doesn't matter which one, but one of them is going to use its lone pairs to form a double bond, pushing the electrons back towards the chlorine atom. And once this pi bond moves here, it's going to expel the chlorine atom. And so now we're going to have our final product, which looks like this. And that's the answer. Now, I do want to mention one thing. Now, earlier I mentioned that the carbon with the chlorine has a partial positive charge because it's attached to an electronegative atom. But there's also another reason why the hydroxide is also attracted to that particular carbon atom. And it has to do with the resonance structure. Notice that the nitro group can pull the electrons toward itself. And so if we draw the resonance form, notice what we have. Okay, this should be like a single bond. Notice that there's a plus charge on this carbon. And so that's another reason why hydroxide is attracted to it. Now, granted, that plus charge is also stabilized by the chlorine atom because the chlorine can donate a pair of electrons to it. So this carbocation is, for the most part, stabilized. Now, another thing I want to mention, let's say if we have a benzene ring. In an EAS reaction, where the benzene ring reacts with an electrophile. Once the benzene ring reacts with an electrophile, it puts a positive charge on the ring. Now, in a nucleophilic aromatic substitution reaction, typically we'll have a halogen somewhere. And as soon as we add a nucleophile, let's say like hydroxide, and we might need like an electron withdrawing group to make this work. As soon as we add a nucleophile, it's going to push a negative charge on the benzene ring. So for nucleophilic aromatic substitution reactions, when you add a nucleophile, it's going to add a negative charge to the ring, and if you add an electrophile, it can add a positive charge to the ring. Now this, of course, on the bottom, that's the reaction that proceeds through the Meisenheimer complex when you have this carbanion intermediate. For the benzene intermediate, you don't have the negative charge, it's just a triple bond. So now, let's review what we've just learned. So go ahead and predict the major products for the following reactions. So if you want to draw the major product, simply replace the halogen with the nucleophile. So the nucleophile that we're adding is NH2. So we're just going to replace the Cl with NH2. Now, for the second reaction, we're going to react the second compound on the bottom with NaOH. So all we need to do is replace the Cl with the nucleophile with the OH. And so the NO2 is going to remain there. And for the last one, we just need to replace the nucleophile, which is OCH3, which is the methoxide ion. We got to replace it with the Cl. Now, which of these is associated with the benzene reaction, and which one is associated with the Meisenheimer complex? Now, for you to get the Meisenheimer reaction, you need an electron withdrawing group. So you need a nitro group. So therefore, the one with the electron withdrawing group is usually the one that proceeds via the Meisenheimer complex. So that's these two. If you don't have an electron withdrawing group to facilitate the reaction, you need to use a very powerful base/nucleophile, and that's NaNH2. And so this is the one with the benzene intermediate. So let's spend a few minutes reviewing aldehydes and ketones, reactions associated with them. So let's go over some old reactions on how to make aldehydes and ketones. Let's say if we have a primary alcohol. If you mix a primary alcohol with PCC, you can oxidize it into an aldehyde. Now, let's say if you have a secondary alcohol, and if you use another oxidizing agent, it could be PCC or even chromic acid, you can oxidize the secondary alcohol into a ketone. So that's one simple way of how you can make an aldehyde and a ketone. Now, you can also make it starting with an alkyne. So let's say if we have propine, and if we choose to use this reagent, which is very similar to BH3, this is like the hydroboration oxidation reaction. The overall effect for this reaction is that it's going to give you the aldehyde. Now granted, it passes through the enol intermediate, but in the end, you're going to get the aldehyde. Now, if you were to use mercury sulfate with water and sulfuric acid. Initially, you're going to get a double bond with an OH group, but this enol is going to tautomerize and turn into the ketone form. So that's how you can make an aldehyde and a ketone from an alkyne. So if we have an acid chloride, we can also make a ketone if we use the Gilman reagent. If we use CH3 to copper lithium. So what's going to happen is the Cl is going to be replaced with one of the R groups, in this case a methyl group. And so that's another way in which you can make a ketone from an acid chloride. But let's go over the mechanism for this reaction, or at least a simplified version of the mechanism. So one way you can see this is that the methyl group attacks the acid chloride, and initially you get this tetrahedral intermediate, and then the oxygen uses one of its lone pairs to regenerate the pi bond, expelling the chlorine group, and that's how you get this ketone. Now, if you want to make an aldehyde from an acid chloride, the reagent that you need is dibo. And what's going to happen is we're going to replace the chlorine with a hydrogen. And so that's how we can make an aldehyde. So now let's go over the mechanism. So we're going to have an aluminum atom with a hydrogen and 3 OR groups. So that's the dibo reagent. So the hydride is going to attack the acid chloride. And we're going to have an oxygen with a negative charge. And then this oxygen is going to expel the chlorine group, and that's how you can get an aldehyde. By the way, you can also use dibo on the ester to convert it into an aldehyde, and you can use the Gilman reagent on an ester to make a ketone. The ester and the acid chloride, they react in a similar fashion, but the acid chloride is more reactive than an ester. By the way, the video that you're currently watching is the 2-hour trailer version of a longer 5-hour video. So I'm going to post a link where you can access the remaining portion of this video if you want to. So feel free to check that out when you get a chance, and let's continue on with our lesson. Now let's say if we have a nitrile, and if we add a Grignard reagent to it, what do you think is going to happen? Let's say if we add methyl magnesium bromide. Now, whenever you have a carbon attached to a metal, that carbon has a partial negative charge. And the carbon that's attached to a nonmetal usually has a partial positive charge. So those two carbon atoms are attracted to each other, so they're going to react and create a carbon-carbon bond. And so the methyl is going to attack the nitro group, and so the triple bond is going to be a double bond now. And the nitrogen atom has 2 lone pairs, so it has a negative charge, and the methyl is attached to it. Now magnesium has a +2 charge, and bromide has a -1 charge. So therefore we can form an ionic bond. When this lone pair combines with the magnesium, if you add the 2 charges, -1 and +2, you're going to get +1. So right now the magnesium has a +1 charge. And what we could do is we can combine the bromide and the magnesium. So this could combine with the Mg. So we can write the product like this. But keep in mind though, this bond is really like an ionic bond. So this is an imine, but this is the salt of an imine. Now if we add H3O+, the nitrogen is going to be replaced with an oxygen, and so it's going to turn into a ketone. So that's how you can make a ketone from a nitrile using a Grignard reagent. Now let's say if we have an alkene, what's going to happen if we add ozone with dimethyl sulfide? Now this is the ozonolysis reaction where the alkene will cleave, and on both sides we can add an oxygen. So on the left we have a ketone, on the right we have an aldehyde. So that's how you can make a ketone and an aldehyde from an alkene, is by using ozone. So now let's talk about the enol ketone tautomerization reaction. So here's the ketone, and it can convert to the enol form, which looks like this. Now the ketone form is usually more stable than the enol form. But how can you show a mechanism for the conversion of the ketone to the enol form under basic conditions? So this hydrogen is called an alpha hydrogen, and alpha hydrogens are relatively acidic because the conjugate base is stabilized by resonance with the carbonyl group. And so this hydroxide ion is going to abstract the alpha hydrogen, and the carbon-hydrogen bond is going to break. Those electrons will be used to form the double bond, causing this pi bond to break. So we're going to get something called an enolate ion, which looks like this. And then the only thing we need to do now is react the enolate ion with water. Because hydroxide grabbed the hydrogen, it's been converted to water. So this oxygen is going to grab a hydrogen from water, regenerating the hydroxide-based catalyst, and that's how you can get the enol in basic conditions. Now, what about acidic conditions? How can we propose a mechanism to get the enol under acidic conditions? Let's say if we use an H3O+, how can we do it? So the first thing that's going to happen is the ketone is going to react with H3O+. Whenever you have an acid, the first step is usually protonation. So the oxygen of the ketone is going to grab a hydrogen from H3O+, and so it's going to become activated. And then water is going to act as a weak base, and it's going to go for the alpha hydrogen. So it's going to grab the hydrogen, form a double bond, and turn this into an OH, or a single bond OH. And so that's how we can get the enol under acidic conditions. Now consider these three compounds that I'm going to draw. And what I want you to do is draw the enol form of each of these compounds and determine which one has the greatest percentage of the enol tautomer. So to draw the enol, simply convert the double bond O into an OH. That's step one. Then step two, put a double bond next to the OH. So for this diketone system, we only need to convert one of them into an OH. But I'm going to draw it like this. You can probably tell there's something special with that one. And for this one, so I'm going to turn the double bond O into a single bond OH, and then I'm going to add a double bond. So notice this turns into phenol. So the one with the highest percentage is phenol. The reason being is this particular enol is aromatic, and aromatic rings are very stable. So this is one of the rare cases in which the enol isomer exceeds the keto isomer, or the keto tautomer. Now this one is going to have the lowest percentage, because there's nothing that's really stable about this enol form. So the equilibrium will shift greatly to the left side. Now, for this one here, the ketone form is still favored, but the enol form is fairly significant. This enol is not only stabilized by conjugation between the double bonds, but it also has this intramolecular hydrogen bond that also stabilizes as well. So, I don't remember the exact numbers. I believe it's like 85-15%. I believe 85% is in this form, and maybe 15% is in that form. But you can double check those numbers, but the keto form is still better. And for this one, it's like 99.9% in the ketone form and maybe 0.1% in the enol form. And in the case of phenol, almost 100% is in this form because it's aromatic. So this is the one with the highest percentage of the enol tautomer. So now let's talk about the Wittig reaction. So let's say if we have a ketone, and if we react it with an ylide, what is the product of this reaction? So the Wittig reaction, sometimes some people call it the Wittig reaction. This reaction is very useful for converting ketones and aldehydes into alkenes. And so to draw the product of the reaction, all you really need to do is replace the oxygen with the CH2 group. And so the answer is going to look like this. So let's try another example. So let's say if we have cyclohexanone. And sometimes you might see the ylide in a different form. Let's say if it looks like this, where the carbon has a negative charge and the phosphorus has a positive charge. Now keep in mind, this is simply another resonance form of the other ylide. So this lone pair can go over here. And so basically this is the same as this compound. So you can see it in any one of these two forms. So all we need to do is replace the oxygen with this portion of the ylide, and that is going to give us our answer. So it's going to be this particular compound. So that's the alkene that's going to form in this particular Wittig reaction. Now sometimes you might get a reaction where they'll give you the reagents to make the ylide instead of providing the ylide itself. So let's say if we have butyllithium, ethyl iodide, and triphenylphosphine. So these are the reagents that are needed to make the ylide. So here's a quick way to get the ylide. It's going to be PH3, P. Then look at this ethyl iodide. Let's draw it out. It's a CH3 attached to a carbon that has two hydrogens and an iodine group. So all you need to do is get rid of a hydrogen and an iodine group. And what's left over, simply attach it to the phosphorus. So this is the ylide. It's going to be CH3. So that's the short way, or the quick way of getting the ylide. So all you need to do is look at the alkyl halide that you have, and the carbon that has the halogen, take away the halogen and the hydrogen from that carbon. And then that's going to be the group that you're going to replace the oxygen with. So the answer for this reaction, this is going to be the compound that's produced. But now let's work through the mechanism for this reaction. Now, the first thing we need to do to show the mechanism for the Wittig reaction is we need to react triphenylphosphine with the alkyl halide. Triphenylphosphine is basically a phosphorus atom with 3 benzene rings attached to it. Now, the phosphorus atom is going to attack the carbon that has the iodine atom, and so those two will combine. And so we're going to get this structure. Now, this carbon with with the iodine, has 2 hydrogen atoms attached to it. So we're going to draw it out like this. Now, whenever phosphorus has 4 bonds, it's going to have a positive formal charge. Now, the next step is to react this with butyllithium. Now, butyllithium can also be written this way. The carbon that is attached to the lithium, or that's next to it, that carbon has a negative charge, and it also has a lone pair. So it's a very powerful base. Now, the carbon with the hydrogen that's attached to the carbon, that hydrogen is relatively acidic because the conjugate base is stabilized by resonance. So the CH2 with the negative charge is going to act as a strong base, removing this hydrogen and put in a negative charge on the carbon. So now we have the ylide. This is one resonance form of the ylide. This is the less stable resonance form, or the one that's more reactive. And now this lone pair is stabilized by resonance. It can delocalize into this bond. And so here we have the major resonance contributor of the ylide. And so it looks like this. So this is the phosphorus ylide. And this is called the phosphonium salt. The iodine atom, or ion, pairs up with the positive charge of the phosphorus atom. Now, we're going to react the ketone with the minor resonance contributor, the one that's less stable or more reactive. We're going to react it with cyclopentanone. So what we have is PH3, P, single bond. It was CH3, and this carbon has a negative charge, and the phosphorus has a positive charge. Now, for the carbonyl group, the oxygen, which is more electronegative, bears a partial negative charge. So the carbon is partially positive. So this nucleophilic carbon with the negative charge is going to attack the partially positive carbon, and so we're going to create a carbon-carbon bond. And so now we're going to have an oxygen with a negative charge, and this is going to be attached to a carbon. Now this carbon has a hydrogen and a CH3, and it's also attached to a phosphorus atom, which has 3 benzene rings attached to it. Now the phosphorus has a positive charge, so this intermediate is called the beta-ene. And now you can see that the oxygen is going to attack the phosphorus because opposites attract. And so we're going to get an unstable 4-membered ring, which is going to decompose very, very soon. So what we now have is called an oxaphosphatane group. So let's make some space, and before we go into the next part, we need to talk about this a little bit more. So let's review something. When carbon is attached to an element that is more electronegative than itself, let's say a bromine atom, Carbon has an electronegativity value of 2.5. Bromine is 2.8. When the carbon-bromine bond breaks, because bromine is more electronegative, bromine is going to take away the electrons when that bond breaks, so carbon will be left with a positive charge. And so that's how we can get a carbocation. Now, when carbon is attached to a hydrogen, carbon is more electronegative because hydrogen has an electronegativity value of 2.1. And so when this bond breaks, the electrons goes towards the carbon atom, and so carbon develops a partial negative charge. So whenever a bond breaks, the electrons always goes towards the one or towards the element that is more electronegative. So now, understanding that concept is going to help us to draw the appropriate arrows. So right now, we know that we're going to get an alkene. That means a double bond has to form between these two carbon atoms. And so this system is going to separate like this. But how should we show the arrows? So what this means is that the carbon-phosphorus bond is going to break and the carbon-oxygen bond is going to break. Let's focus on the carbon-phosphorus bond. Now, carbon has an electronegativity value of 2.5, and phosphorus is like very similar to hydrogen, it's about 2.1. So because carbon is more electronegative than phosphorus, when the carbon-phosphorus bonds break, those electrons are going to go towards the carbon atom, so it's going to move here. Now, if we compare the carbon atom and the oxygen, oxygen is more electronegative than carbon, and so when the carbon-oxygen bond breaks, those electrons are going to go towards the oxygen atom. And so we need to draw the arrows like that. So therefore, we're going to get this product, this particular alkene, and we're also going to get triphenylphosphine, which is a side product. And so that's the mechanism for the Wittig reaction. Now let's talk about the formation of hydrates from aldehydes and ketones. So this is formaldehyde. It's the simplest aldehyde, and it has two hydrogens. And when it reacts with water, it's going to form a hydrate, which is basically a carbon with two alcohol functional groups. And notice that the arrow is bigger when it faces the right side. The equilibrium constant for this reaction is about 2000. So it's product favored. What this means is that the hydrate form is more stable than the aldehyde. Formaldehyde is it's very reactive. It's not very stable. Now, let's say if we take acetaldehyde, also known as ethanol with an Al, this reaction is fairly reversible, so to speak. And the equilibrium constant is very close to 1. So I'm just going to round it and say it's about 1. So you get like a 50-50 mixture of the hydrate and the aldehyde. Now, if you have a ketone, the situation is different. The reaction is reactant favored. And the equilibrium constant is very small. It's like 0.002. So what this means is that ketones are less reactive than aldehydes. And now let's understand why that's the case. There's two factors that you need to consider: steric factors and electronic factors. So formaldehyde is more reactive than acetaldehyde, which is more reactive than acetone, which is the simplest of the ketones. So let's talk about the steric factors. So the reason why formaldehyde is more reactive than acetone is because acetone has these bulky methyl groups. And so it's going to be very difficult for a nucleophile such as water to approach and attack the carbonyl group, because the methyl groups block approach. They pretty much protect the carbonyl group from a nucleophile. So that's one reason why acetone is less reactive than formaldehyde. The second reason is because the methyl groups are weak electron donating groups, and so they can donate electron density to the carbonyl group. Now, keep in mind, because the oxygen is partially negative, the carbon of the carbonyl group is partially positive. And so if you donate electron density to a partially positive carbon atom, it's going to be less partially positive. It's going to be more neutral, so less electrophilic. And if you want water, which is a nucleophile, to react with the carbonyl group, it wants to react with an electrophilic carbon, not a neutral carbon. So the more electrophilic the carbon is, the more reactive it is. So because methyl, the methyl group is more of an electron donating group compared to hydrogen, it's going to make the ketone less reactive. So whenever you add an electron withdrawn group to a carbonyl group, the carbonyl group becomes more reactive. But if you add an electron donating group like a methyl group, it becomes less reactive. So those are the two reasons. Steric factors, the methyl groups are bulky, and the other reason is electronic factors. The methyl groups can donate electron density to the carbonyl group by means of the inductive effect, making it less electrophilic. So, with that in mind, which of the following three ketones is most reactive? So which ketone is most reactive? So here we have two very, very bulky groups. Those are tert-butyl groups. Here we only have one. And here we have just two small methyl groups. So therefore, because this group is so bulky, this is going to be the least reactive. Now, acetone doesn't have any bulky groups relative to the other two compounds. So therefore, this is going to be the most reactive, because the carbonyl group is most accessible. Here, it's going to be extremely difficult for a nucleophile to approach that carbonyl group because of all these methyl groups. So now, how would you propose a mechanism for the formation of the hydrate under acidic conditions using H3O+? So what's the first thing that you think we should do? So feel free to pause the video and try this example yourself. See if you can propose a mechanism. So the first thing that's going to happen is the carbonyl group is going to grab a hydrogen from the acid. Now, water, at this point, once H3O+ loses a hydrogen, it turns into water. So now water is going to act as a nucleophile. It's going to attack the carbon, causing the pi bond to break. And so what we're going to get at this point is a structure that looks like this. This is going to be an OH. And here, here's the water that we added to it. So right now, water has a positive charge. So now we need to use another water molecule to remove one of the hydrogen atoms. And so now we have the hydrate, which we can write it like this if we want. So that's how you can show the mechanism for the formation of a hydrate. So next, we're going to talk about the formation of the cyanohydrin functional group. So let's say if we have a ketone, and if we react it with HCN, what do you think is going to happen in this reaction? So the ketone is going to grab a hydrogen. Let's grab it from HCN. So now the ketone is activated. And then the CN minus is going to act as a nucleophile, attacking the carbonyl group. And so here we're going to have an alcohol and a nitro group. So this is called a cyanohydrin group. Now what's going to happen if we add H3O+ to this product? H3O plus is going to convert the nitro group into a carboxylic acid by removing the nitrogen. And so what we now have is an alpha hydroxy carboxylic acid. And plus, we're going to get the ammonium ion as a side product. Now the reason why it's called an alpha hydroxy carboxylic acid, let's redraw the structure. So let's say this is carbon 1, 2, and 3. This structure can be redrawn like this. So the alpha carbon is the first carbon away from the carboxylic acid. That's the alpha carbon. This is the beta carbon. So we have an alcohol, which is also known as a hydroxy substituent, and it's on the alpha carbon, so that's why it's called an alpha hydroxy acid or an alpha hydroxy carboxylic acid. Now what's going to happen if we react a ketone with a primary amine? What do you think is going to happen? Now the reason why it's a primary amine is because there's only one carbon atom attached to the nitrogen. Whenever you combine a ketone or an aldehyde with a primary amine, you're going to get what is known as an imine, specifically a substituted imine, one with an R group. And all you need to do is remove water. So basically, you're replacing the oxygen with this part of the molecule. And so you get an imine. Substituted imines are also known as Schiff bases. Now the imine, it forms under mildly acidic conditions, so you may need to add a weak acid. Typically, the best yields occur when the pH is somewhere between 4 and 5. Now let's say if we were to add a secondary amine, so one that has two carbons attached to it. So if you add a secondary amine or amine, you're going to get an enamine, which is going to look like this. Instead of having a double bond between the carbon and the nitrogen atom, there's going to be a single bond. And we're still going to have the two R groups attached to the nitrogen atom, but the double bond is going to be between two carbon atoms, and this is called the enamine. So if the nitrogen has at least two hydrogens attached to it, you're going to get the imine. If it only has one hydrogen, then you're going to get the enamine as the product.